Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, we're live. So we'll get started here. So there is still some material in the lectures this week. I'm not expecting you to, digest a lot of this in detail for exam purposes, but it's important to say a few things to sort of round out the course. So what I'm going to do today is have another little look at a way of criticizing the orthodox logic and another picture that one might have of how reasoning could be done that would result in differences to the system, but a rather different style to the things we looked at last week. And then tomorrow I'm going to say some bits about how we can prove things in these systems, what's provable, what isn't, how proofs go, and some things about how you can disprove things and show that some classically valid sequence are not provable. So this tomorrow will be a little bit more low-level detail, and that's as far as we will get. But today I want to have a look at another line of challenge to orthodox logic, which we haven't very much talked about. It's been sort of lurking around in the shadows, but we haven't done anything on this in workshops or tutes or lectures. And that is, I want to start by looking at the concept of truth and thinking of a different construal, really, a different sort of worldview, or a collection of them. It's not a unique picture. That's sort of quite different from the standard classical one and gives rise to a different logic. So I want to think of. So I want to think of truth not as an absolute given thing, like there's a real universe out there that we go and discover, and even if we can't discover anything, there's still a fact of the matter. That nature is arranged for everything to have a truth value in this kind of as a completed. A whole thing, right, as a complete sort of given object. That's the standard absolute, notion of truth that we have to really work with if we're going to do classical logic. But of course, there are other pictures of that, and what I want to consider is the idea that truth might be given by or relative to a state of information. Relative to a state, and then there may be many states, many possible states, not just the one, and the idea is that there is no absolute universal given truth outside that. Okay, so we'll think of a proposition as true if it's justified or warranted or supported by the information in a given state. Okay, and there's no assumption that any particular state of information gives you a decision about every proposition. right? They can be partial. And there are lots of, notions of truth that are more or less like that. Ooh, the radial menu, how exciting. I suppose if we click on this thing, it goes away, yeah. So the idea is going to be that we have these various states of information. We might have, it's some information here, and there might be a different state of information, somewhere else. There might be a bigger state of information that could include both of those, and, another one that includes one of them but not the other, and so on, right? I mean, there could be many of these, right? And in general, we're going to consider what's true in a particular state or true given a particular state of information, and not suppose that there's this big sort of absolute universe out there that's got this sort of fixed and complete, of which these particular states are partial descriptions. That's not the idea. Okay, the idea is that the information that exists is what's been constructed. So it goes along with ideas of truth along, the lines that in part we constructed as we go along. And this is perhaps something that makes more sense for mathematical truth or something like that than it does for truth about physical objects, because you don't get to construct, well, you get to construct tables, but you don't get to construct the truth of the fact that it hurts when you walk into one, right? I mean, whereas if we're talking about a mathematical domain, that hasn't been constructed yet, there's no reason to think that the universe and nature out there has already fixed the truth value of everything about that, and all we've got to do is discover it, especially if, some of the things about that are not even decidable after we've constructed it, right? I mean, in virtue of what could nature fix, all the truth values of everything in a domain like that? So this is another picture, okay? And we take it that there are a few general principles about these things. So that if P is true in a state S, right? If P is true in a state S, then it's going to stay true. Then P is going to be true in all states that extend S, right, of S. So if P is true in this little state here, right, if that gives us enough information to warrant the assertion of P, then it's also going to be true in this big state here, because that includes everything that we've got in the little state. So we're going to have this kind of heredity property that when you construct more, you don't lose anything that you constructed before. Okay, that's one principle. The general idea is that further construction is always possible, right? I mean, the universe is never a completed whole thing. It's always like a work in progress. And this is the picture. Okay, I mean, we don't have to pin this down very exactly. It's just that there are plenty of views of truth about some domains that are of this general sort. Then we can say a few things about how connectives and so forth work, and quantifiers. Well, I won't talk about quantifiers today, but take a formula of the form A and B. I mean, that's true in a state S, we may suppose, if and only if A and B are both true. In S. That's how conjunction works. It's the same. I mean, the story doesn't change, right, for conjunction. And in a sense, it doesn't change for disjunction either. although this means that we've got to gloss the picture a bit. So we take a disjunction A or B to be true in a state S, if and only if A is true. I keep writing ins in S, or B is. So disjunction is going to be truth functional as well, but truth here is, truth given by a state of information. Now, of course, if we think of information as we're normally sort of accustomed to use that expression, then we might be justified in asserting a disjunction where we're not, where we don't know, nothing tells us which disjunct. I could give you the information that either A or B is the case without telling you which. But the sort of states we're talking about here and the concept of truth that goes along with them is, they're more sort of full than that, right? We're thinking of these states at least as closed under sort of all possible investigation or something like that. So, a disjunction doesn't get to be true unless one of its disjuncts is. Even where that truth is, is relative to a given state. So the story about disjunction is the same as the classical story, but of course, if we extend to a bigger state, then more things will get to hold. Now, what about the conditional, though? This is where the stuff gets interesting. So that's true in a state if and only if what? Well, what does it say? Right, this is going right back to week 2, I think, when I introduced implication, connective. And I said, what does it mean to assert if A then B? It means that I'm in position, the background information, which is the state of information here, gives me all I need to argue validly from A to B. Right? So one of the things that's been constructed in the state, that if the conditional holds there, is some way of getting validly from A to B. That's part of what the state gives you. And if a state gives you that, then any extension, any bigger thing that includes that state, will still give you that same warrant. Right? That persists along with everything else. Okay, so we need the arrow elimination inference from if A then B and A to B, this is a detachment inference, modus ponens as they call it. That's got to hold not only in the current state where we're evaluating this thing, but that's got to persist in all the extensions of the state. Right? Otherwise, if we were to go to a bigger state where more things were true, if A got to be true, right, and we had this warrant for getting from A to B, but B wasn't true, then we'd have a available inference that goes from something that's true to something that isn't, and that's no good. Right. So the implication, if A then B, is true in a given state, if and only if B is true in all extensions of S in which A is true, including S itself. If A is true in S, then B has to be true there. But if A isn't, then we may have to look at all the extensions of S, and some of them may make A true, and we look in all those. Is B true everywhere there? If so, then yeah, we have this warrant for getting from A to B. But if not, if there's a counterexample in some extended state, then that conditional can't be true. Okay. So the connectives are still this kind of truth functional things. Right? You tell me the truth value of A and the truth value of B, I can tell you the truth value of A or B, I can tell you the truth value of if A then B, and this kind of thing. right? But we may, for the conditional, we may have to look at possible extensions of the state and not just at the state itself. Right. So it's a logic still very much along the classical lines. The same motivating talk will do, right, for all the connectives that I used at the beginning when I was introducing these. But it's just that you've got to remember now that when I say true, I'm not talking about some fixed absolute notion. I'm talking about truth as given by a particular set of constructions, really. Okay. And that changes the logic. What about negation? I haven't said anything about negation here. Classically, in standard logic, negation is somehow in a sense it's the central connective, right? It's because negation tells you what clashes with what things disagree, and in a way you can see the whole logical inference in the classical picture as sort of driving away from contradictions. I mean, resolving them, making things consistent. I mean, this is how the negation rules work, right? You derive a contradiction, you say, so one of those things must be false, and that drives you forward, right? That's sort of what's driving the whole logic in a way. On this kind of picture, negation is relegated to a kind of peripheral role, right? It's really the positive stuff, really the implications and the disjunctions and this stuff that's driving the logic, and negation is sort of sitting out on the side. And that goes along with the semantics. Classically, we only have this one notion of truth, sort of fixed universe, what nature provides. And nature just provides P or it doesn't, and if it doesn't, we say not P. It provides not P. Right? But on this picture, I mean, a particular small state of information may just have nothing to say about P. Right? I mean, it doesn't. P may not be, true, may not be guaranteed as true by that state, but there may be some bigger state of information where P does get to be true. So we don't want to say that not P was true, was forced by the small state, because then that would be inherited by the bigger state, which would then be inconsistent. That's absurd. Right. So the usual way that negation gets introduced into this kind of logic is we think about the false constant, and we say that that's not true anywhere in S for any state. And then not A just is, by definition. A implies the bad thing. Okay. We can do this classically as well, right? I mean, that's sort of how the classical rules get motivated. This absurd proposition, the false, has this kind of, it goes together with negation like this. And we can still do that. And it follows from that, we get truth conditions for negation. We get that not A is true in a state if and only if A is not true in any extension of S. Right, I mean, it has to be the case that A is not only isn't true, you just don't have enough information to get you A, but that you never can, right? I mean, you actually got a construction in the little state that rules out any bigger state in which A got to be true. Right. So that's the semantic story. That's a complete semantic story for this kind of logic. But I want to try and make things a little bit more concrete, so we can we can have a little picture that we can operate with a bit. So I'm going to look at a very small example of this sort of semantic picture, and try and make some points. So suppose we only had two states to consider, right? A little one and a big one. This is the smallest non-trivial example of this kind of thing, right? I mean, there is a smaller example. That's where we only have one state. That's classical logic, right? That's just, you know, ordinary truth tables. But this one, we take it that we've got a, you know, a little sort of the stuff that's been constructed and is available at some point, and then there's a bigger state that will happen when some more stuff's been constructed. I mean, some more truth has been added. Right, so the big state is going to give us more truths than the little one. If we take any particular proposition, P, it could be inside here. Right, it could be true in the little state and in the big state as well, of course, because it inherits everything in the little state. Or it could be out here in the outer darkness somewhere. You know, plain straight out false, right? It never gets to be true even after we've expanded our horizons, right? Or it could be in the interesting case where it's not, there's nothing in the smaller state of information that warrants the assertion of it, but when we've extended, then the truth of P has been constructed. Right? So that's the intermediate case. And of course we can think of those in a way that's familiar to you if you've done the workshops on these things as 3 truth values instead of 2. Right? There's the 2 extreme values, the one for the dot in the middle and the one for the dot, you know, in the outer darkness. And there's this intermediate one, right, where whether P is true or not depends on which state you're talking about. All right, we can have some names for those. Right, we can call this one true, I suppose, and this one false. And this one in the middle, intermediate, I. Why not? I don't want to call them 1, 0, and a half because that confuses it with another picture, because this thing in the middle is not a half-truth. It's just completely true in the big state, and it's completely false in the small state. Right? This has got absolutely nothing to do with vagueness and all that. Right? It's a different... Right? This is scene 2, a different part of the forest. There's no... You've got to kind of forget the deviant logics that we were doing last week. This is how to do, you know, the standard classical reasoning with a non-standard theory of truth. Right? It's trying to do the same kind of logic, but with a more, some might say, a more refined notion of what truth is. So we can think of, you know, how conjunction works on these values, for example, is straightforward. You know, we've got 2 propositions, A and B. They can be truth, false, or this intermediate thing. And, you know, it's fairly obvious that, well, if one of them's false, even in the big state, then so is the conjunction. And if they're both true, even in the small state, then so is their conjunction. And otherwise, if we go, you know, from one state to the other, the conjunction is not true originally because in the small state, because one of its conjuncts isn't, but it is true in the big state because both of its conjuncts are, and so this is I. And disjunction is very similar. Okay, it's what you'd expect. It's the dual connective. Right, I mean, that's true if one of the disjuncts is, even in the small state. The only way it can be false in the big state is that neither disjunct is true there, and otherwise it's intermediate. And this is fairly standard 3-valued tables, which you can use just like the 2-valued ones to evaluate, you know, to make up truth tables for formulae. And you are familiar with that if you did the workshop on it. And if you didn't, that's your fault. You were invited. Yeah. Needle. Now, what about these other things, though? what about the implication connective? What does that look like? You know, this is across the top, that's B, and down the left-hand side, that's A. And in the matrix here, we want the value of if A then B. Well, it's like the classical story, but, you know, with two of them. So if B is true even originally, it's going to stay true forever. The inference from A to B, it doesn't matter what A is, that's always going to preserve truth, right? So immediately we can fill in the left-hand column. And if A never gets to be true, even when we've expanded things, then the inference from A to B preserves all the truth there is, because there isn't any. Right? So any old thing preserves that. There's nothing to preserve. So for the same reason as the classical story, we have truth on the bottom line. So again, this is nothing to do with relevance and the use criterion for validity and, you know, opposition to vacuous discharge and all that. Vacuous discharge is fine, we're happy with that. Right? So there's nothing deviant about, you know, structural rules for this logic. It's a logic in a way in the classical tradition. What about the middle? What if both A and B are in this intermediate state? Okay, so initially neither of them hold. So the inference from A to B, you know, preserves truth because it's vacuously, you know. But once we've expanded, well, then B holds. All right, so the inference from A to B preserves truth there. So in that case, this is simply true everywhere. What else have we got to fill in? Well, if A is true even originally, and B is never gets to be true, then the inference from A to B can't ever get to be true, right? Because it'll always fail to preserve the truth of A. On the other hand, if B gets to be true in the big state, then in the big state, the inference from A to B will preserve truth, will it? Yeah. But originally it doesn't, because B isn't true. Right? Initially A is true, but B isn't. Right? So that doesn't preserve truth initially. But when B gets to be true, then it does. So in that case, the conditional gets to be true later on. But in this case, what we get in the case where B never gets to be true, but A eventually does, right? Then in the bigger state, or in both the states, in fact, the inference from A to B fails to preserve truth everywhere, and so this is going to turn out to be false. Okay? Because, yeah, A eventually gets to be true without B ever being true. Okay, so now we've got these tables and we've got a definition of negation as implying false. False is the right-hand column here. So if we've got A, we can define not A, we can get the value of not A from that. True IF. If we read down this column, that's F, F, T. So we can see that the negation of this intermediate value I is F. Okay? And if we do the double negation trick, if we negate that again, we don't get back to I, we get to T. Okay, so our logic, this is the first point at which the logic we get here has departed from the standard classical system. Right? Double negation elimination is no longer a valid principle of inference on this story. Right? Because if A is right here, if A is here, not A is here, and not A is here. So not A doesn't entail A, because we've got a state here, this smaller state, in which not A holds, but A doesn't. So that's a classically valid sequent, classically valid inference, that's no longer any good. So this thing starts to be interesting after all. It's not just a complicated, long-winded way of getting classical logic back again. Right? We do get something different. Right. Not A, not P, for instance, does not entail P. We can't validly derive P from not P in this logic. Other things that are different, obvious difference, is not a theorem that P or not P. Because, again, in the little state of information, okay, it may be that neither of them is justified, right? I mean, it doesn't be... If they're both in this intermediate case, right, if P has this value I and not P has the value F, then P or not P also has this value I. And that means that there is a state in which it's not true. All right. So that's another... Again, these logics are starting to diverge. Classical logic has one sort of attitude to this stuff, and these so-called constructive logic has a different account. Now, so much for that bit of the story. This being logic, we also want to say what the deduction rules are. We want to say, what does this do to our natural deduction calculus? How do we have to change things to get this logic instead of classical logic? And this time, it's very simple. Right? To do these deviant stuff that we did last week, you had to complicate things. You have to have two different ways of putting premises together and remember which goes with which and then what rules you can use to move them around on the left-hand side and all that. But in this case, in the case of this logic, things are extraordinarily simple. All right, so if we just start with our ordinary natural deduction system that's familiar to you, right, we simply drop the rule, double negation elimination, because it's not valid, as just observed. And keep everything else, right, or elimination, vacuous discharge, all the rest of the stuff, right? You keep it all. Just drop double negation elimination. That gives you a logic. It's not exactly the one I've just outlined. It gives you a system called minimal logic. Right. So minimal logic, all the positive rules, all the rules that don't mention negation, they're all exactly the same as classical ones. All right. So any proof, any classical proof that hasn't got negation in it is valid in minimal logic as well. Okay. What's minimal logic say about negation? Well, we still have negation, elimination, negation, introduction rules. Okay. They're still around. They're good in minimal logic. Those rules say, you know, that if from A and not A, you can get bad, and that if from A you can get bad, then from whatever else was around you can get not A and discharge assumption A. You know how negation introduction works. Now those rules, remembering that by negation here, we really just mean A implies bad. All right? These rules, if this is A implies bad, all right, that's just an instance of arrow elimination. right? And if this is A implies bad, or if this is bad, then that is bad. Take that off again. Make that, do this the right way around. That's bad. Okay, so if not A there means A implies bad, that's just an instance of arrow introduction. That's what I wanted to say. So in minimal logic, the negation rules are just implication rules. They're just a special case of the implication rules. You have this bad connective, this thing that you write as an upside down T sort of thing, but you don't have any rules, any particular principles about it. It could just be any proposition, like Q or something, right? The introduction and elimination rules for negation, they're just a special case of the rules we've already got for implication. So minimal logic, it's really only the positive rules, right? It's really only conjunction, disjunction, implication. Well, and the quantifiers, but right, and it's got this kind of pretend negation, right? The negation is just sort of implying something, but we're not telling you what. It's whatever you feel like denying today, right? The bad thing hasn't got any special properties. Sometimes occurred to me that this ought to be something like the logic of politics, you know, where what's false is just whatever you feel like denying today, you know, whatever is convenient. That gives you some sort of theory, but you would really like negation to have rather stronger properties than that. And you'd like that, you know, this absurd proposition, you know, what was it supposed to be? Right, it was supposed to be, it's supposed to be complete absurdity. So if you've got that, you better turn around and, you know, and start rejecting premises and things. Yeah, the phrase I used for that was that than which nothing sillier can be conceived, right? I mean, it's so bad, it's the worst proposition you could have. In mathematics, it might be 0 equals 1 or something. Not sort of conceivable. So, in order to get the full logic that we're after from this, we've got to make a second move. Right, we've got to add some special postulate, some special rule concerning this bad guy. And what we want to say is that that's the absolute worst proposition in the world. It's so bad, it implies all the others. Right? So we want to add a sort of elimination rule for this thing. Bad elimination or something, that just says that from the bad thing you can infer arbitrary A. Okay, and this is sometimes called the absurdity rule. So that's this false constant is not just any old proposition. It's right down at the bottom. It's the worst thing there could be, and that fixes it as a particular proposition, and that fixes negation as a particular operation, not just you know, implying some arbitrarily chosen thing. The better way to do this, I'll just give myself a little bit more real estate here. Maybe a better way to do this is to strengthen the negation elimination rule. Now it says if you've got a contradiction, you've got A and you've got not A, you can infer arbitrary B. I mean, it comes to the same thing, right? I mean, the old rule says you can infer bad, and the absurdity rule says if you've got bad, you can get B. So we can collapse them into one rule and just strengthen negation elimination to do this. It's sort of, you know, and it'll strengthen RAA as well. It'll build in the vacuous discharge stuff, and you know, in a lot of proofs, reductio RAA and double negation go together, you know. And in some of those cases, we collapse the two into one, and we can use this negation, this stronger negation elimination rule instead. And that gives you this other interesting logic, which you see all over the place in the literature if you read about these things, called intuitionist logic. Right. This is, that's an S, and that's a T. Intuitionist logic. And this is a system, a non-classical system of logic that's been around quite a while. I mean, it was first proposed back in, I don't know, nearly 100 years ago, and then formulated properly a little bit later, I mean, in full detail. And it's been extensively investigated. It's a very interesting logic. I'll just mention a few of the things we can prove, and maybe even have time to prove something in this system. But you can see what the proofs are like. I mean, the proofs in this system are not surprising, right? They're just classical proofs, except you're not allowed to use double negation, and you do have a slightly more generous negation elimination rule. Or you can build that strengthening into RAA as well if you want to, in the obvious way. Yeah, I mean, we can still prove things like if P then not Q entails if Q then not P. That's still valid. Intuitionistically, okay, how would we do that? Not sure I ever have proved this. Let's see. We'll assume if P then not Q. It's a standard proof, so we'll assume Q for the purposes of arrow introduction. And we want to prove a negation, not P, so we'll assume P. And of course get not Q. That's from 1 and 3. That's just arrow elimination. Then what? That's 1 and 3. What we want is we want to get not P from 1 and 2. So, but we can do that. We've got a contradiction. Or let's go through the two steps of the negation rule. We can get bad, if you like, from 2 and 4. Negation elimination. This works in minimal logic, you know, 1, 2. So this is a valid proof even in minimal logic. It doesn't require the absurdity rule. And then we're going to keep 1 and 3 and discharge 2. Not Q. Sorry, no, we're going to keep 1 and 2. 1 and 2, discharge 3, not P. From 5, discharging 3. Negation introduction and discharge 2. All right, from line 6, and assumption 2 gets discharged. Arrow introduction. So it's a classical, it's classical proof. All right, it doesn't use double negation elimination. So it's a valid proof in minimal logic. It's valid in minimal logic, so it's intuitionistically valid. So this one's fine, right? Nothing new, except we're just careful not to use double negation elimination. However, we can't prove if not P implies Q, then not Q implies P. No, that's not provable. And if you try to prove that, you'll find that you just inescapably need double negation at the end. You assume if not P then Q, you assume not Q, right? You assume not P, you get Q, then you've got Q and not Q, so you can deny your assumption. That gives you not P, and you're stuck. All right? You can prove if not P then Q implies if not Q then not P. That's fine. But you can't reduce the not P to P. All right, you really can't, and you can show, that this can't be done. So, some things that are equivalent classically are not equivalent intuitionistically, and that includes some of the De Morgan laws, for instance. So we do have that not A and B, so not A or B, we do have entails not A and not B, but the other way, not A and B, does not entail not A or not B. Right, it may be that A and B, there's no extension of our state of information where A and B both get to be true. It doesn't follow that not A is true now, or that not B is true now. Right, because there may be some futures where A gets to be true and some where B gets to be true. Right, I mean some bigger states. So, so some of these things that look equivalent classically are not intuitionistically equivalent. And we can't prove, of course, P or not P. It's just observed. There's no reason why some state of information should give us a decision. I mean, it's not intuitionistically. We don't make the classical assumption that every question has a correct answer. Right. But we can prove, interestingly enough, the double negation of that. As you can very easily observe by looking at the classical proof of P or not P and just don't do the double negation at the end. Right? That's provable. So the intuitionist is not somebody who denies the law of the excluded middle. He will fight to the death anybody who wants to deny the law of the excluded middle. He says, no, it's not the case that P or not P. But then you say, so P or not P? He says, why? I haven't seen any argument for that. Right? P or not P can't be false. You can prove logically it can't be wrong. But the intuitionist sees no reason to go on and say that it's going to be true then. Right? Because it doesn't believe in double negation. Right? The fact that something isn't false doesn't imply that it has to be true. It may be undecided or something. So briefly then, why is this an important logic? Well, this is, in a way, this is the most important of the non-classical logics that I've mentioned in this course. We've not had time to go into it in enough detail, which is why I deferred it until the last week. But it's a very important system. It's important philosophically because there's a big debate in philosophy, in the philosophy of language, between realist views and anti-realist views, if you look in the literature. And the anti-realist views go along with intuitionist logic. These are views based on some kind of verificationism, the idea that for something to count as true, there has to be a way of verifying it, at least in principle. Otherwise, it would just sort of get beyond the scope of what we could do in a human language. And people who have taken that kind of view find that they are led to intuitionist logic rather than classical logic, and so this is a focus of some of that debate in philosophy, which is the most important debate that's been going on in philosophy of language of the last half a century or so. So it's important logic for that purpose. In computer science, it's a very important logic, but I haven't got time to tell you why. It yields a model of computation. If you want to go and look up sort of entry terms to the literature, look for the Curry-Howard isomorphism. Magic phrase. Intuitionistic proofs yield programs in a certain sense. That's very hand-wavy. I mean, that's a very cryptic remark, I know. But it is the case that this kind of logic is deeply embedded in theoretical computer science. And it's important in mathematics because it's the foundation of the whole research program, the whole view of mathematics as constructive. And constructive mathematics, the question even for a classical mathematician, the question of whether something has a constructive proof is interesting and important. Constructive means you don't prove that things exist unless you actually can construct an example of it. Or you don't prove that a disjunction is true unless you actually can prove one of the disjuncts. So you don't have these proofs of the existence that just show that they couldn't fail to exist. Not enough. You